Okay, so since yesterday we are a little bit over time, so I didn't show you how to run all the codes we learned really in RStudio. So today we will begin by catch up a little bit by showing you how to run all the codes we learned yesterday in RStudio. So first, you just I have already installed the tidyverse on my own R, and you can load it by using the library I have already learned. And then you set the working directory to the folder to avoid typing all those very long full paths of the files. Then what you can do is you load the data into your from the external CSV, into your into R. And then you will see some message here. They are not big arrows. It's just a few messages from the read CSV function. And if you don't want to see them, just as it has already said, you can use the argument to set it to quiet. And then, as I have told you yesterday, it's a good idea to preview your data to ensure it is indeed loaded correctly. So the first way of doing this is by using the head function to just see a few first six rows of your data. Another more interactive way is just by clicking the variable holding the imported data frame, and then a window will pop up, and then you can check it in a more interactive manner, like what you will typically do in an Excel spreadsheet. And then we can use a for loop to count the percentage of failed reads, and it's only like fewer than 1%, so perfectly fine. And you can also vectorize to replace the for loop with just one single line. And the results will, of course, be the same. And then we learned how to remove a column by either using the minus sign to remove the column, or to just specify which column we want to keep. So after deleting the column, I save it into a new variable. And as you can see here, we no longer have the first column versus before. So this is before. This is after we use select to remove the first column. Okay, then we can keep moving on. So we can add another column for subtract the background from our raw reads. As you can see, it's added here by the mutate function. And then we can add some further columns to indicate the condition and replicates associated with each read. Now you see the drug column and the replicate column we want to add is already there, but they appear at the most right part, the rightest part, which is a little bit counterintuitive because we usually want these columns to show like before the reads, so we can associate it with each read, which means we want to reorganize the order of our column. And again, as we have already seen yesterday, we can do it by using the select function again, but this time we just select based on the order we want. And after this, you see the drug and replicate column. Yeah. Oh, yeah. And the drug and the replicate column will go into the right order you want based on how you select them. And then we move on to calculate the mean and standard deviation by grouping every 3 replicates together. Again, you can do this with a for loop, but just be careful when you're using the for loop. You need to consider the fact that you need to group every 3 replicates together, which adds some extra complexity to your for loop. But I hope you can gradually get used to such kind of complexity. And of course, DPLYR offer us an easier way to do it without even using for loop. Instead, we use the group by function and then tell the group by function which column we want to group our data based on that column. Here we specify it to be drug, such that when we later calculate the mean and standard deviation, all the rows are grouped together based on the values in drug. So if they are all three columns have the value control in the drug column, then they will be grouped together for calculate mean and standard deviation. And this is exactly what we will do next. Oh, sorry. I think, yeah, I forgot to click this one. Yeah. So I save it into a new data frame called drug screen data processed. And as you can see, we now have the mean and the standard deviation pop up again to the right on the right hand side. Then you may like we explain what's the magic hidden behind the group by function is it's secretly attach an attribute to your data frame, and you can check this attribute by using the groups function. And as you will see here, drugs pop up, which means you are grouping your data frame based on what it is in the drug column. And then, of course, like let's say like later you don't want your data to be grouped like this, you can always ungroup it. And then if we check again, this attribute becomes empty, which means no group at all after we use the ungroup function. And then finally, yesterday we say that, okay, so although this kind of way of presenting your data is fine, but it's a little bit counterintuitive to read because every three like row has the same mean and standard deviation, which can be a little bit confusing. And at the same time, it's also very long. You need to scroll down a lot so as to like read all of them. And in this case, what we can do is we can use the pivotal wider function in tidyr to switch it into another format. I will show you the format first. So we have this. And as you can see, now it's the same data frame, but we just reshape it into a wider format. Well, all the the replicates belongs to the same condition are stretched from one column into multiple columns such that you can read all the data for one condition just within one row. So this is typically for most people, this is more intuitive way of presenting the data, the wider format. Okay, and as this function's argument is a little bit difficult to understand, so I will just give you a review here. So first, we tell the function like what are the columns you want to stretch into the wider format. That's in the values from argument. Then, because you are creating some new columns, usually you want to give them a meaningful name. That's what the names from and the names prefix argument is doing. Names from means which which column should the new column names get parts of its names from. And like it's quite easy to understand that we want it to get part of its name from the replicate column, because previously these rows are all about different replicates. And in case you feel that just the number the number in the replicate column is still not enough, you are always welcome to add some prefix to that value to make it even clearer. That's what the name prefix argument did. So the final column names in the converted wider data frame is like this. So the first part, the read or read minus BG is from the original column names before it's stretched out. And then the second part is coming from the prefix. And the final part is coming from the replicate column. And finally, in the first argument, we delete the sample ID column. And the reason is because this column is unique for each row in the long format, which makes it incompatible with the wider format of presenting the data. So that's why we delete it. The drug column is fine because for every 3 row, the value is exactly the same. So when we stretch it, we can just collapse all the same reads into one row. So that's why the drug column can still be kept without any problem. Okay, so we stop here yesterday. So we will move on our journey to day 3. So let's just switch to hope it works. So for the students on Zoom, sorry, can some of you guys just confirm you can see the slides moving and yeah, oh, perfect. Yeah. Good. So let's start with today's goal. So today we will learn a few more functions from the tidyverse. And another very important part is that we are going to work with not only just codes and text, we will visualize our data by some graphs. And in the final part, it's not related to writing learning new functions or new packages. It's some tips from myself on how to make sure your code is easier to read, use, and maintain. So turns out if you ask something that I really regret, I didn't learn very well when I pick up R, it's actually tip 3. So the section 3, how to write the codes in a good manner. So I never regret about not learning certain functions, but I really regret I didn't learn to write the codes very clear when beginning to learn R. Okay, so first let's continue from section 5 to learn more about the tidyverse. So yesterday we learned pivotal long or wider to convert a long data frame into a wider format. And if there is a way to go in one direction, there is usually a way to go back. So that's the pivotal longer function for converting a wide data frame into a long data frame. So again, let's have a look at this function. So I will again explain to you what each argument means. So the first, I think the first argument I would explain to you, the drug screen data wide is just passing the data frame. So it is quite easy to understand. Then in the COLS, which is just abbreviation of columns argument, you supply to it what column now you want to squeeze into one column, into the long format, because we are now going from wide to long. Like during long to wide, you tell it which column you want to stretch out to make it wide. Now, if you want to go in the opposite direction, you just tell which column you want to squeeze so as to make it from wide to long. And clearly here, we want to squeeze whatever we stretch out, which is the read replicate 1 to 3 and read minus BG replicate 1 to 3. So here the semicolon is just a convenient like a convenient symbol offered by tidyverse to allow you to specify multiple columns in a like arranging in a continuous manner without typing each one of them out. So you can do like this 1 to 3 and minus 1 to 3 without the need to type out each of the column. You just need to specify the start and the end. And then the names to argument let you specify the name, because now you are going to combine multiple columns into one columns. You are going to clear some columns, right? So then who is going to hold the information contained in those column names of those cleared columns? So this is to tell it to add a column that holds all this information contained in the column names that got squeezed out. And this is and you can specify whatever name you want. So here I just name it reads info, which means information related to each read. And finally, you are going to squeeze all the columns into a new column. And what's the name of that column? That's the values to argument you can specify. Here I just call it reads. So let's take a look of what will happen after you squeeze the column, after you convert it to wider, longer format. So this is the original wider data frame we pass to the pivotal longer function. And here is the output. So first, it's indeed longer, like less wide. And you can notice that all of the reads are squeezed, all of the reads here are squeezed into the reads column. And then all of the column names are squeezed into the reads information or reads info column. But it's a little bit different from what we start from, right? In our original data frame, before converting to this wider format, we have a replicate column, which reads 1, 2, 3, 1, 2, 3, right? And we have, and another thing is that we instead of having only one reads column, we have reads and reads minus background. But for here, reads and reads minus background are all squeezed into this reads column. So it's not very ideal. We want to make it even clearer. So here is a more advanced way of using the pivotal longer function. So clearly, in the simplest way of using it, we only have the choice of squeezing all the columns we specify into one column. But here we want to squeeze all the columns we specify into two columns. So how can we do that? How can we do that? Is we use the names pattern function together with the dot value keyword. So let me explain to you how this works in detail. So first, we should notice that our columns names, thanks to the good practice of naming it, has some pattern. So it's always read or read minus BG plus replicate plus the replicate number. So whenever we have some like characters with a very well-defined pattern, we can always extract a specific part out of that pattern by specifying the naming pattern in a way called regular expression. So first of all, what is regular expression? So it's the argument we supply here. It can be a little bit confusing at first glance, but I will explain to you what's going on. So let's begin from the left-hand side, which is here. So so this power sign, this triangle, sorry, what do you, sorry, what do you?
It's called carrots.
The character sign. Yeah, the character sign means start, which means marks the start of your pattern, and the dollar sign at the end means the end of your pattern. So and then the dot followed the period start means anything. So together with the character sign, it means my text, my character first starts with anything. By anything, it means any like letters, any special characters, all possible stuff. And then we come to a part which we can recognize, which is underscore replicate underscore. So it means after starting with anything, then there will be a replicate underscore replicate underscore in my text. And then if we further move towards the end, the /D means a digit. A digit is something like 1, 0, 1, 2, 3, 4, 5, 6, 9, 0. And here we have /D plus. So the plus sign means it can contain more than 1 digits. So if you use /D, it means only 1 digit. But if you are not sure how many digits there will be, you can use the plus sign, means 1 or more than 1 digits. And finally, the dollar sign, again, marks the end. So what it reads is that you are telling R that my column's name have certain pattern, and the pattern starts with anything and then reach, can I finish? Sure. And it starts from anything, and then in the middle, it will have underscore replicate underscore, and finish with a digits of any length. Yeah.
By anything, so that dot star can be any data type.
Oh, here it's a character. So you are using this to handle characters, but it can be like exclamation mark. It can be essentially anything you can type on your keyboard. Yeah. And then you also see there is something that like the round bracket. So round bracket means what I want to extract from my character based on this pattern. So it essentially says it starts with anything, and please R extract that anything out for me. And you also see a round bracket with the digits. It means there will be arbitrary number of digits at the end, and please extract that arbitrary number of digits for me. So if we apply the whole expression, the whole regular expression to our column names, what R will extract is read and 1 from read replicate 1, because 1 is the digit and read is the anything that it starts with. And similarly, if you have read minus BG, again, it's the anything before the replicate. So it will be extract out first, and then the digits at the end will be the second one to extract out. Okay, so now we understand the names pattern. Like we essentially pass in a regular expression. And by the way, regular expression is a concept beyond this function. So it's hold true throughout the R. If you have any function asking you for a regular expression, you use the same rule to specify the regular expression. And then we can go to the names to part. So in the names to parts before, we just specify something like reads in for. You may think it's like, how do you specify the columns, the name of the column to hold all the old column names? But here you see the first thing we pass is dot value. And it doesn't mean please create a column whose name is dot value. Instead, this is a keyword. So this is a keyword, which means it must be written in the exact same way to tell the function that please group my columns to be converted into to be squeezed into multiple columns based on the first part that's extracted out from the regular expression. It's the first part because the dot value is the first element in the vector. So it essentially says, okay, so because you will extract read or read minus bg from this first part of regular expression, then you have two values. And when the pivotal longer function see this dot value, it will say, oh, the user want me to split all the columns into two groups, either the read or read minus bg. And then how do you handle the digits you extract by the regular expression? You put it into a column whose name is replicate. Here, replicate is not a keyword, so the pivotal longer function will just create a column name for you, a column name whose name is replicate. And as you can see here, to avoid user accidentally trying to accidentally use this dot value as an intended column name, so they make it very weird by putting a dot in front of the value, such that virtually no one will try to name their column names like this, because typically you just use a word rather than something begin with a dot. Yeah, so just be careful. Like this is a keyword rather than something you can use freely. Yeah. So here is just something about the regular expression. It's a general concept used in programming. So even if you have other function in R asking you for regular expression, as I have explained before, the same grammar holds true. And you will, even if you go to different programming language, they will also have the concept of regular expression, but the exact grammar will be slightly different. And if you want to, if you have a pattern in your mind, and you kind of forget the grammar, and actually the grammar can be even more complex. I just cover part of it. You just describe your pattern to AI, and they are super good at converting your described pattern into a regular expression for you. Just don't forget to tell the AI which programming language you are using. Yep. So what we will have now with our new pivotal wider by using the name pattern together with the dot value keyword is that we essentially reproduce the long format of our original data frame before being converted to the wide data frame. Yeah. So, and perhaps the only thing missing is the sample ID we delete first. I mean, there is no way to recover that back, but all the other things are essentially the same. So, given that now we are, of course, I think right now you have a question in your mind is like, we know the wide format is more reader friendly. Then why do we bother to convert a reader friendly format into a reader unfriendly format? So we will soon see what's the use of the long format when we begin to use ggplot to visualize our data. So here is now, given that we indeed already do lots of reshaping and calculate some statistics on our drug screen data. Now we are ready to pick out the candidates for potential inhibitor and activator. So inhibitor should be the drug that significantly decrease the activity of your enzyme versus the control condition. And an activator, vice versa, should be something that significantly boosts up your enzyme's activity when you are versus the control condition. So we can do this by do a statistical test on the replicates versus the control condition. So here is now we are just going to implement this. So here is two key questions I think you should consider in your mind before I review the answer. So first, we are going to visit like each condition in our data frame. Are we going to use a for loop or should we vectorize? And then the second thing is that now we have our data in two formats. One is the long format, where all the reads are grouped into the long column. We also have a wide format, where each row is just one condition. So which one should we work on to solve this task? So either one perhaps will work, but working with one of the formats would be easier than the other. Yeah, so just take maybe 20 seconds to think about this before I review the answer.
Just checking. Long means like it's vertically longer, while wide means it's horizontally bigger.
Yeah.
Okay.
Okay, so first, the first question is that should we do vectorization or do the loop? So as I warned you yesterday, although vectorization can be very convenient, do not force vectorization when it is not possible to do that. So to do that, I think the key concept, the key step in determining whether we should vectorize or not is whether the t-test function can handle a vectorized input or not. And to know that, I mean, the first intuition is just to read the technical document of the function, as I've told you multiple times before. So as we can see, the accepted input data format is numeric vector. I should remind you that for t-test, it needs to accept replicates for each condition. So that's why it accepts a vector. But now imagine that if you want the t-test to do multiple conditions for you, where each condition contains multiple replicates, then it should be something even more complex than a vector. Because in addition to separate different replicates, you also need to separate different conditions. So an intuition would be the function should accept something that's more complicated than vector. For example, a matrix, where each row is a replicate and each column is a condition. But it seems not. If you don't believe so, you can also ask the AI to further confirm that the function cannot handle something complex like that. So the conclusion is that, okay, so vectorization seems quite difficult because the student t-test function t.test can only handle one condition at a time. So it cannot vectorize to do all the conditions for us all at once. Now if vectorization is difficult, then let's go back to the most basic loop. Then are you going to loop through the long format of the data frame or the wide format of the data frame? So let's think about this. If we choose to use the long data frame format, remember the painful process we go through when we are calculating the mean and standard deviation, right? We need to group every 3 rows together because they belong to the same condition as different replicates. And similarly, we need to do the same thing here if we choose to work with the long format. But if we are looping through the wider format, then that means each row contains all the replicates for one condition. So all we need to do is to take that row out and then extract out all the data belongs to one simple belongs to that condition. And now we are ready for the t-test. So all in all, it means we should choose the wide data format. And in many cases, choosing a good shape of your data frame can significantly increase your efficiency and decrease the complexity of your job. So But at the same time, I want to take advantage of this exercise to introduce you to something new. So we have learned before how to extract like column and row values using the basic way of doing it in R. So I just want to also show you here, how can you do it with tidyverse function. So what we do here is that before jumping into the for loop, just for convenience, I want to first gather the control data, which is just, we are currently working in the wide format. So it's just the first row, and the control data is in the control replicates is in the column read minus bg replicate 1, 2, and 3. So how do we select the first row and that 3 column out of our data frame? So you see here, you see some new stuff showing up. So we do drag screen wide and a vertical line, arrow sign, slice 1, and then another this weird symbol, and then select read minus bg replicate 1 to read minus bg replicate 3. So I think you recognize some function, like say, for example, here, this one is the variable name of the data frame. Here is something like a new function. And here is the select function we have already known, like learned. So first of all, the slice function is the function in tidyverse or dplyr for you to select rows based on which row you want. It's like the friend of select who help you select columns. You select column with select, you select rows with slice. And the most canonical, the standard way of using it is just slice and your data and which row you want to get. And of course, you can also select multiple rows if you want. And this vertical line plus a bigger than sign is something called the pipe operator, introduced in R 4.1.0, but we are using 4.5.1, so you already have the pipe operator built in. So what it means is pass whatever is on the left-hand side as the first argument to the function that's on the right-hand side of the pipe operator. So what actually it does is that like this. Because we need to use 2 functions to select the row and the column, in the standard way, we need to write 2 lines of code. And in each line of code, we need to put in the data frame we want to use as the first argument, which is a little bit redundant. Some lazy people just say, it's too annoying. Like I need to write 2 lines of code and I need to put in my variable's name as the first argument, even though they are the same. And sometimes it can be like more than 2 lines, like 10 lines. So at some point, people introduce the like the pipe operator such that it works like this. So here is my data frame, and then I use a pipe operator to pipe it into the first argument of this slice function, and thus this one here is actually the second argument. And once this slice gives you the output, because it's on the right-hand side, the left-hand side of another pipe operator, then this pipe operator just pipe the output from the slice function as the first argument into the select function. So the read minus bg replicate 1, 2, 3 is actually the second argument. By doing this, you just save yourself from writing multiple lines of code and type in your data frame's name again and again. So that's all it did. If you feel not comfortable to use it, just write 2 lines of code. That's like clear. And to be honest, I sometimes also do that. It's just so that because there are lots of people who are addicted to using this when writing their codes. I just want to make sure at least you can understand when you see it. Whether you want to use it, it's based on your own like choice. A brief history of this pipe operator. So in addition to this vertical line plus bigger than sign, you may also see another version of this pipe operator, which is 2 percentage sign surrounding a bigger than sign. So this is some historical reason. So the idea is that the pipe operator first show up not in R but in one of R's package as a function, and in the package called P2s. And then in 1 year later, another package introduced the symbolic pipe operator, which is this percentage sign surrounding the bigger than sign. And then the developer of the DPLYR package really like this sign and use it a lot, like in the demonstration examples in how to use DPLYR package. And later, as DPLYR package is very popular among data analysts, the pipe operator at the same time also become very popular. And finally, in 2020, the developer teams of R really hearing lots of feedback from users saying that, oh, we want a natural built-in pipe operator for all users of R rather than the user of the DPLYR package alone. So the R team introduced the vertical line coupled with the bigger than sign as the natural built-in pipe operator in R, which means it's independent of any package. When you download it, the R, you have it. There is some subtle difference between these two pipe operators, although they are conceptually and functionally very similar to each other in most aspects. The only difference is that sometimes if like you use the pipe operator to want to like simplify a large chunk of codes of multiple functions into one single line, and you notice that in a very painfully inconvenient manner, one of the function in the middle takes the output from previous step as, say, for example, the second argument rather than the first argument. In this case, what you can do is to use a placeholder, which is underscore for R's built-in pipe operator, or the dot for a period sign for the older DPLYR pipe operator. And then if you are using the placeholder, then you can place the placeholder at whatever argument you want to put the previous output to in the next function. Say, for example, here, I put my second argument, the pipe operator, and then another function. Then you put the first argument here. This time, this argument will jump into the second argument rather than the first one because you have a placeholder here, which will be recognized by R when you are using the pipe operator. I mean, this is even more advanced way of using the pipe operator. And the difference is that for this older one, you need to use dot. Yeah. Okay, so enough about the pipe operator. Then let's go back to our own like data. So once we use the for loop to just adjust the p-value, to calculate the p-values of each condition versus the control group, then the next step here is what we can do something called adjusted p-value to adjust the p-value. So just to assure you, this is purely a statistical practice. It has nothing to do with programming. It's not that R give you some p-values that must be adjusted in a programming sense that so as to make this step correct. It's just statistician told you that it's better for you to adjust your p-values if you are doing multiple hypothesis testing. So ask your statistic teacher why Like if I'm doing a single statistic test, you don't need to adjust p-value. But if you are doing, say, for example, in our case, 200 statistical tests of 200 different drugs versus a control condition, then it's a better practice for you to adjust the p-values. What happens is that you inflate, which means you make your p-value slightly larger such that less values become smaller than the 0.05 cutoff. Or in other way, you need to make your test more stringent than it is supposed to be when you are working on only one test. So again, it's not related to programming. It's only for statistical reason.
I'm assuming that's Benjamini and Hochberg, the BH.
Yeah, Benjamin.
Are there other methods available?
Yes. So if you want to use other methods, so the method here is because there are different ways of adjusting or inflating your p-values. And one of them is the BH. So I actually forgot the name.
Benjamini and Hochberg.
Yeah, Benjamin Hochberg. That's one of the very widely used one. Abbreviate as BHL. I guess you already know how, if you want to know what other methods are available, where you should go to. Yeah, right?
Yes.
So yeah, you can just, if you don't know, you can ask me, but I think you should know. So just given that we are on this topic now, so what's the difference between methods? It's not mainly something like a speed concern, like some tests are really fast, some tests are really slow. It's how stringent it is. Some methods are extremely stringent, such that they tend to throw out lots of p-values that are smaller than 0.05 by significantly inflate them. I mean, these ones are very stringent, which means the ones that are left by these tests that are still smaller than 0.05 should be highly trustable. But there are also methods that are not that stringent, because in most cases, you want to at least have something you can work with from a screening, right? If you have a super stringent test tell you, okay, nothing passed, then you don't have anything to work on. So sometimes people prefer to use a less stringent test. So BH is just one of them that kind of have a balance between stringency and accuracy. So typically I use BH.
What is the, okay, I'm not a statistician, but what's the purpose of like this kind of test if you can just say like, let's arrange the p-values from smallest to largest?
Okay, so that again, it's not related to programming, but from a statistical point of view, if like the student is just asking like, why are we always like pick something smaller than a threshold rather than rank all the p-values and say, for example, pick the first 10 smallest ones. I mean, if you are doing a screening and you are going to verify your results later, then it's actually up to you how you suggest, how you choose the candidates. The rank-based way is also fine if you really want to. But the problem is that if you are using the ranking-based way without an absolute cutoff, you need to keep in mind that it's always possible that your screening doesn't give you anything. So if you are ranked, which means even if they are super terrible, you're still going to test them. And specifically in biology, some of the later verification can be very expensive and time consuming to take. So that's why in most cases, people still want to have an absolute threshold to give them huge confidence and incentive to spend money and time to verify the candidates out of the test. Yeah. So another thing we are typically interested in is to use, in addition to whether the drug significantly changed the enzyme's activity, again, it's a statistical reason. We are also really interested in by how much time, by how much fold does the drug change the activity? If the change is significant, but it's only by 20%, perhaps it's not very useful. But if the change is significant and it's by 5 times lower or 5 times higher, then it's a very good inhibitor or activator. So we can do this again by using the function we have already learned, which is mutate and our data frame. And then we add a column whose name is log2fc, which is just the abbreviation of log2 fold change, which means we take the log2 of the mean of each replicate for each condition over the mean of the control condition to calculate by how much fold does it change against the control. Okay, then the next thing to do is that we want to pick out our candidates from the 200 drugs, let's say based on the adjusted p-value. So again, I will use the most widely used and also highly criticized threshold, but still most widely used, the 0.05 p-value. So here we introduce a new function in dplyr for helping you do this. That is the filter function. What you essentially do is filter, give it a data frame, and give it the column name you want to thresholding based on, which is the PADJ column, and pick out all those rows whose PADJ is smaller than 0.05. And after we pick out all the candidates with adjusted p-value smaller than 0.05, the next thing we can do, if you want, we can also sort the output based on their log2 fold change, such that the highest one, the most, let's say, the one with the largest log2 fold change pops up at the beginning, and the one with the most negative change pops up at the end. So what you can do is use the arrange function to sort your data frame based on the column you specify. And when it comes to sorting, there is always two ways. The first is based on an increasing order or the decreasing order. So for here, if you want sort, arrange, always sort in the increasing order. But if you wanted to sort in a decreasing order for you, you just use the DSC function, which is abbreviation for descent, and apply this function to the column you want to sort, such that this descent function essentially just add a minus sign to the column. So the biggest become the most negative. Then when you sort it in the increasing manner, it's actually in the descending manner. So that's all what the descent DSC function does, but of course, it doesn't modify your original data. And finally, once we pick out all the values we have, we want to do, like all the values based on the p-adjust, we can export our results to a new CSV files. That's because for R, all those variables are stored in the RAM of your computer. So if you close your R without specifically saving all those variables, then you lose all of them. Now, given that we spend a huge amount of time analyzing this data, let's save our output into an external file, so we always have it. And we save it as a .csv because if your supervisor, if your collaborator want to have a look at it, they can still open it in their favorite Google Sheet or Excel. And for you, you can still re-import them into R by using the read CSV function. And for here, if we want to use if we want to export our CSV files, we use the write CSV function again from the readr package. This time, again, the first argument is the data frame you want to write to CSV. And then the second part is just a character specifying the file name of your file, of the CSV file you want to be. And just one thing to emphasize is that in addition to a pure file name, it can also be a relative path, which means a relative path, like after you set in your working directory to get it into a subfolder in your current working directory. Or you can also use a full path as the file name to direct it to a specific folder based on the complete full path. Yeah. So up to this point, we essentially finish the data reshaping, analyzing, and exporting part. So the next section or the next subsection we will go to is to visualize or analyze the data. So before that, so I will just show you how it really works in the RStudio to give you a sense. So share screen to RStudio. Okay, so for those on Zoom, can you see the RStudio scrolling and working? Okay, perfect. Thanks for confirming. So we will start from the let me see. So we will start from, okay. So we will start from the pivotal wider part. So first, just we use the simplest form of the pivotal longer function. If we run it, we will have, let me just show you, right? So this is what we have seen before when we use the pivotal longer in the simplest form, where all the reads are squeezed into one column. And if we use the more advanced version with the name pattern and dot value keywords, what we end up have is now our column will be split into two columns based on their names, or more specifically, the first part of their name. And our replicate number, which is the last part of the column name, will automatically go into a new column based on what we specify, which is the replicate. Okay. Then we move on to the calculation of p-values, which is this part. As we have discussed before, we should work with the wide format because it's easier to work with the wide format. And here is just the pipe operator for getting the control data. And we loop through it. And in each loop, we apply the t-test to each drug versus the control data. And finally, we extract the p-values from the t-test result by using the $sign plus p dot value. So this is just something specific to the t-test output. So let's just run this part. And then use the mutate to add the p-values calculated to our drug screen data white. Perfect. So now we have the p-value available here as the last column. So the first row is NA because we don't calculate control versus control, which is meaningless. Yeah. Okay. Then the next thing we can do is we add another column for adjusted p-values. you see a new column pops up as the last column, which is PADJ. And as you have already noticed, that the PADJ value is significantly larger than the corresponding P value, which means the method inflated. And given that we are using the same cutoff, that's 0.05, this means our selection becomes more stringent after we adjust the P value. And again, we can also add a log2 fold change column to our data. The log2 fold change is here. Oh, so one thing I forgot to mention. Because you first calculate the fold change and then take log. So for log, any value larger than 1 will be positive. Any value smaller than 1 will be negative, just high school math. So any value positive, any fold change larger than 1 means the activity is increased, so it's a potential activator. Any value smaller than 1 means the activity becomes smaller, so it's a potential inhibitor. And after log2, a potential activator will have a positive log2 fold change, and a potential inhibitor will have a negative log2 fold change. Yeah. Therefore, we first okay. So here there is actually something new, but yeah, let's skip this part first. So again, we can reorganize our columns. Oh, yeah, sorry for that. Oh, yeah. So I shouldn't skip this part. So here we add a new column. So based on what I've told you before, so based on the whether it's positive or negative, so what we can do is that if the p-value is smaller than 0.05, we will regard it as a potential activator or inhibitor. And if its p-value is smaller than 0.05 and the log2 fold change is smaller than 0, then it means it's a potential inhibitor. And if it's the p-value is smaller than 0.5 and log2 fold change is larger than 0, then it's a potential activator. So we just want to add a column indicating the screen results of our of our analysis. So we add this column, and why I don't have this in the slides? Yeah. Okay, so sorry, for here I will just run the code first, and after the break I will explain to you what this part means. So essentially it's just add a new column to it based on the screen results. And then what we can see here is that now we have a screen results column based on p-value and log2 fold change. Finally, we reorganize all the columns such that the most important columns will pop up first, which is the log2 fold change, the p and adjusted p-value, and screen results by using the select function. And then we can filter our because it's still like lots of rows. And for people who want clean results of only the candidates, we can filter out based on adjusted p-value. So by doing this, we will have only those significant potential inhibitors or activators. And to make things even easier for our reader, we can sort it such that the log2 fold change is in a decreasing order, whatever shows up at more towards the top is the stronger activator. And whatever is more towards the bottom is the stronger inhibitor. And finally, we can either direct the output as a CSV file to the current working directory, or using a relative path to write it to a subfolder in the current directory. Yeah. So after the break, I will explain to you what's the meaning of this function, and we will start to learn how to do data visualization. And before I let you go, just one thing I must do, otherwise the manager will kill me. So please evaluate the course by scanning the QR code you have, because this is our last class. So yeah. For people on Zoom, can you see it? The QR code. Are they all go for the break or? Oh yeah, okay, perfect. Thank you. Yeah, then we will take like 10 minutes break and gather back at around 3. I think 2:53. Yeah. Yeah, thank you very much. So can everyone on Zoom see the R Studio interface? Okay, perfect. So I will just explain to you how to, how does this function works. Turns out for some whatever reason, I think I make the slides, but somehow I cannot find it. So the purpose of this part of the code is that we want to add something to conclude our screen as the screen results. And it's pretty easy. We just separate all of our drugs into 3 groups, either a potential inhibitor, a potential activator, or simply no significant effect on the target enzyme based on the p-value and the log2 change. So first of all, I think like you can immediately it can immediately come into your mind that you can use the for loop together with the if statement to do that. So it's like you first cycle through each row, and then if p-value is smaller than 0.5 and the log2 change is larger than 0, then it's a potential activator and blah blah blah. But here I just want to show you a more convenient way of doing this by using the mutate function we learned before together with the case when statements to be used together with the mutate function. So what we do is that we first have we first have a logical vector indicating whether each row is a potential activator or a potential inhibitor by using this logical operation we learned before. So we first have whether the p-value is smaller than 0.5, and we'll then calculate whether the log2 change is smaller than or bigger than 0. Then we use the logical operator AND to join them together such that we have an AND condition based on these two logical values. And as I should remind you, so this is because this is one column, this is another column. So the final output, say for example, the potential inhibitor is a vector of true or false, and vice versa, and similarly, the potential activator. And then once we have these two logical vectors, the next thing we can do is that in this, we first, in the mutate, again, we introduce a new column whose name is screen results. And then in this screen results column, we want to fill in different values based on the true or false value from potential inhibitor or potential activator. So potential inhibitor, so the grammar is like this. Case when if potential inhibitor is true, then we use the wavy line, means if this is true, please put this value inside the corresponding row. And similarly, if potential activator is true, please put potential activator. And finally, we have this true here. It means if you evaluate this one, it's false. If you evaluate this one, it's false again. Then finally, for everything else, we just put a true here, because for any one that doesn't get true in the previous two lines, it will always be no significant effect. So the true here is something equivalent to else. Because if all the conditions you want to check and still nothing matches, for everything remaining else, put no significant effect. So what this will give us is, sorry, what's the variable name? Is this column. So based on what is in the p-adjust and log2 fold change column, we fill in different values to this screen results column. So this one will also be useful once we use ggplot to visualize our data. Yeah. So this is just a way to show you how you can combine mutate with the case when function to replace a for loop plus an if statement. Yeah. So let's switch back to my favorite package, which is ggplot. Okay, so for everyone on Zoom, just double check. Can you see the slides? Okay, perfect. So in the first, now we analyze that we finish analyzing the data. But typically, when you want to publish a paper or you want to present your results to other people, you cannot just throw a CSV files onto their face and say read it yourself. They typically prefer you to have some easy to understand, and in many cases nowadays, beautiful plots for them to easily grab a sense of what you are doing. So that's what we will do with this ggplot package, that ggplot2. So it's part of the tidyverse universe and is specifically dedicated to drawing graphs or in a more precise manner, data visualization. And I will teach you how to use it by plot two figures with you using ggplot. So first, let's do figure 1. So how to demonstrate like how all the we identify the candidates out of the pool, but how can we show other people how we do that? And the essential idea is that we are using log two-fold change and adjusted p-value to group our results into 3 categories: potential activator, potential inhibitor, and no significant change. And given that we have 2 variables, the log2fc and p-adjust, and lots of data points, so a scatter plot with one axis as log two-fold change, the other axis as the p-value sounds like not a bad idea. So first, let's begin from some simple ggplot. So to use the ggplot, you first start with a function. You almost always start with this function, ggplot. And then as the first argument, you tell it, okay, which data set I want you to plot based on, and it's our drug screen data, right? And then in the second argument, you typically give it something called AES, the output from another AES function. So AES is abbreviation for aesthetic, which means it's something dealing with the aestheticity of the graph, or in other words, just how the graph looks like. And one important thing about how the graph looks like is who is the axis and who is the y-axis. So here, what you are essentially saying is that x equal to log2fc means using the column whose name is log2fc in this data I give you as the x-axis, and similarly for the y. And then after finishing this ggplot function, ggplot already knows what data you want to work on and which column of the data you want to put onto which axis. But still, it doesn't know what plot you want to make. It can be a line plot, can be a scatter plot, can be a bar plot. So that's what we specify here with another function, which is geom_point, which means we plot our data as point, then it's a scatter plot. Then how do we let ggplot knows the geom_point function? Here is something very special about ggplot2's package's own grammar. You use a plus sign to join 2 functions together. So this is the grammar for the ggplot2 package. So it's not universal for other functions in R. Only in ggplot you do this. You use the plus sign here to join 2 functions together such that they modify the same graph. So as you may already guess, so if you want to plot different types of plot, you always have a different function like geom histogram for histogram, geom box plot for box plot. And this is what the plot it give you look like. This function will generate this plot out for you. So let's look at this. So of course, this is not beautiful, to be honest. And there are actually some problem with this graph. First, you don't have a title. It's a good practice to tell your audience what you want to show as a title, right? And the second, we are using like some abbreviation like p-adjust or log2fc here. Sometimes for those like very professional audience who already know this abbreviation, it's fine. But usually we also want to have the freedom to change what's on the title of x-axis and y-axis. And another thing, as you may notice, so although we are typically interested in those candidates with small p-values, our plot is largely dominated by those very large p-values from 1 all the way to 0.25, right? But to be honest, this range we are typically not very interested in because the p-value is too large. Then let's make some change to our ggplot by adding some more stuff to it. So first, how to solve the problem of not having a title? We can use another function called ggtitle to specify the title we want for our plot as a character. And again, you use the plus sign to join it to the core ggplot function. Similarly, if you want to change what is written on the x and y axis, you can use the xlab and ylab function and join them together with the plus sign. One last thing, how do you solve the problem of the dynamical range of the y-axis? A typical way of doing this is to run a log transformation on your axis when you feel that your axis focus too much on the absolute change rather than the fold change. So what does this mean? It's because, think about this. If your p-value changed from 0.2 to 0, although the difference is only by 0.2, the meaning is huge, which means it changed from something that's perhaps not very significantly different to something with a p-value close to 0, means they are very, very likely to be different. But at the same time, this 0.2 change can mean nothing if it's from 1 to 0.8, which means anyway, they are very likely to be similar to each other. So in this original, like normal scale, we focus too much on the absolute difference, which is like 1.0 to 0.8 means similar for like to 0.2 to 0. How do we solve this problem? We can run a log transformation on the y-axis because the log of 0 is minus infinity. Then the smaller the p-value is, the larger it is, and the larger the difference is. And another thing is that if you run a log transform on something smaller than 1, which is typically how p-value looks like because they are probability, then everything becomes negative, which is a little bit not intuitive for people to understand because people typically like, if something is more important, please make it more positive. So that's why we add a minus sign before the log transformation to make everything positive again. So for log transformed p-values, the smaller the p-value, the larger the after the transformation, which becomes very intuitive to understand. The larger, the better. Yeah. Sorry. Okay.
Why is it that the no significant event things have a very small p-value? Or like, sorry, a very large p-value?
It's just, this means the probability of them being similar to the control condition is large.
Right. Oh, okay.
Yeah. So it's just the statistical meaning of p-values.
Understand.
Yeah. So you can see after this graph now looks much better. So all those not very important, not significant candidates just crowd into the bottom part. We don't care too much about them. And we can immediately see there are 5 candidates clearly show up at the top part of the graph. Additionally, we have more detailed x and y axis title to explain to the audience what we are drawing here and together with the title. But we can make our plot even more informative. That is, we can color each data point to show the audience what's the screening results we assign to each data point. So to do this, and this is exactly the reason why I create a column whose name is screen results to indicate the screen results in the original data sets. So what we can do now is that we add one more argument in the aesthetic function, telling it how you should color each data point based on the values from the screen results column. So in the screen results column, we have 3 categories, and the ggplot function will assign a different color to each category. Say, for example, you see here, the potential inhibitor will be assigned blue, and then this one is red, this one is green, and a legend explaining what color is assigned to which group will automatically be added to the ggplot. So this is how our graph looks like now. But here, as you can see, although we specify please color our data point based on this column, we didn't tell what color you should use. And the consequence is that ggplot, using the default color, it stores as the default values. Like, I don't know how you feel, but at least for me, this is a little bit counterintuitive. So the least important stuff is colored red. And typically we want something like activators. We want it to be like red or some very warm colors because it increases the activity. And for the inhibitors, we usually think, oh, it would be more intuitive if we have a colder color, means decreasing in activity. But anyway, you just shouldn't highlight something not important with red, right? So then the next question is that, can we tell ggplot which color we want to use for each group? And the idea is that we use a named vector to tell ggplot what it needs to use for each of our group. So we have already learned what is a group. So, a vector. So a vector is just a collection of characters or numbers. So here we specify the color as a vector called group colors. One thing you may notice is that these characters is highlighted. So RStudio automatically does it for you if it detects that you are typing in something that matches a color. So it's not me doing that. RStudio will automatically do that for you, just to give you a sense of what this color looks like. And then I also define something called the group order as another vector, and make this group order the name of our group color vector, which means each element in our group color vectors now have a name. So Salmon has the name potential activator. Sky Blue 3 has the name potential inhibitor. And gray has the name no significant effect. And once we pass this named vector group colors into another function called scale color menu as the values argument, and join this function using the plus sign again to the ggplot function, ggplot will assign the corresponding color to the corresponding category in the screen results column based on the group color vector. So that's how you decide which category gets which color. You use a named vector whose name of each element correspond to the name of that category. And another thing you see is the name equals to null. So name just means the title of the legend, which is this screen underscore results. Here I set it to null, just means no title please, because I think the titles, the legend's text already explain what it itself is. And another thing, as you can see here, so when drawing the legend, it first shows up no significant effect, then potential activator, then potential inhibitor. So it's fine, but for someone who's very picky like me, I prefer them to have the no significant effect at the last, because again, it's the least important one. So how do you specify which legend goes out first, which legend goes out last? Remember that when we learn the variable type factor, on first day, I told you that factor can be very useful. So here is another example of how factor can be useful. So what we do to change the order of how the legend text is specified, we make, in our original data, we make the screen results column as a factor, and we specify the level of that factor as the group order. Potential activator, potential inhibitor, no significant effect. Then by doing this, the legend text will be plotted out as the exact order of the levels of the factor. So how do you, like, whenever you want ggplot to plot something in an order you want, you make that something a factor and specify the order as the level of that factor. Okay, so more about specifying colors in R. Like sometimes I've spent a whole afternoon picking up colors for my plots to make them perfect. So there are two ways for you to specify your color. So first, you can use something called the hex code. So this is something this is a universal standard across different platforms. If you have a hex code of your color, you can use it in Photoshop, in PowerPoint, or in R. So it's the universal language invented by people who want to share different types of colors. And if you say this is too difficult to memorize, R also has several built-in colors you can choose from. And each of them has a very intuitive name, like Seymour. Yeah, my favorite red color. It's not that red, but it's also red in a way that makes people feel comfortable. When you type it in R, as I mentioned before, if it recognizes that this character matches a built-in color's name, it will automatically highlight it for you with the color. But don't worry, this doesn't mean these words are reserved keywords. You can still use them as a normal character. Say, for example, as a column name. Say, for example, if you have some data set dealing with Simon, and one of the columns must be named as Simon. Don't worry, it's not reserved keywords. You can still use it like this. It just RStudio will then again highlight your column name for you by thinking that it's perhaps you are trying to use a color. So it's a little bit weird, but don't worry about that. It's unlike true or false or if and for, which are reserved keyword that you cannot use.
What color is true? No, I'm kidding.
No, yeah. So actually, so far, I always use scatter plot to refer to the plot we are making, but they have a more commonly known name called volcano plot. And actually, what I show you is we gradually reproduce how to draw a volcano plot, which is a very commonly used plot in big data in biology, where you have lots of measured features and you want to show people by what standard you use to pick out the candidates. And if you have lots of data points, it typically looks like something like very concentrated in the bottom and very spread out as going towards the upper part of the graph, which makes it like an erupted volcano. So it get the name volcano plot. Okay, so in addition to showing the audience, how do we pick out our candidates from the large pool? It's also a good practice to show the audience that within only the candidates, they are indeed significantly different from the control. So now we forget all those non-significant data points. We want to focus specifically on those picked candidates. And we want to show that indeed the mean activity is significantly different from the control condition. So what type of plots is good for this? So in my opinion, a bar plot is good. So let's think about how sometimes before you making a plot, you perhaps need to like add some to make some changes to your data set itself. Say for example, I have a feeling where the case one function is slice is. So say for example, if we use our original like data frame where all the results non-significant or significant are there, then we will have something like 200 bar plots, like 200 bars, which is super crowded and difficult to visualize. So what we want is to start from something that's cleaner. So if you remember, we have something called, when we export the CSV, we export two CSV. So the first one is the complete one with all the data points. And the second one is the one that we filter out only the candidates, which have only around 5 or 6 rows. So clearly, it's better to use the filtered drug screen results rather than the unfiltered one. And because we already save it as an external file, so even if you close R before you go back again, we can read it in with the read CSV function. But at the same time, just keep in mind, we better also show the control condition. So we can add the control condition back to our filtered candidates data frame by using the add row function. You simply says, please add this row, which I get from the complete data frame to my candidates data frame. Okay, then let's start. So again, we start from the simplest, because this time we want a bar plot rather than a scatter plot. So we change geom point to geom bar. And we also add GG title and for the X title, so we don't need anything because the tick. So just some terminology. So this control drug 002, 009, 014. So these ones are not called title. So these are called ticks. Similarly, 0, 25, 50, 75, they are ticks of y-axis. The title is recorded activity of enzyme AU. Yeah. So the only thing different from geom point and geom bar is that in geom bar, you must specify an argument called stat, which is the abbreviation of statistics. So this is just a convenient way for you to plot different kinds of bar plot but, with different types of statistics. First, stat equal to identity means I give you the column, just plot the bar plot whose height corresponds to the exact value in that column. Don't do anything else for me. This is what the identity means. But in some cases, people might have a column where they have different categories, and what they want the bar plot to show is the number of each category as the height of the bar plot. So which means they don't have the raw data, they don't have the data ready for the bar plot, which is the height of the bar. So, but in this case, you don't need to manually calculate it on your own. You can use the stat equals to count, which means for the y-axis, I give to ggplot for bar plot. Instead of plotting out its raw value, please count the number or the frequency of each category and use that as the height of bar plot. And you can do something even more fancy by saying that using the summary together with another argument called fun, which is abbreviation for function. That is like, it is like a more generalized way than count. It means apply the function I specify in the fun argument to the y-axis column and use the output of the function as the height of the bar plot. So it's more advanced use. Perhaps at first you'd better like just calculate the stuff on your own, and when you get more like experted at R, you can begin to use these more advanced functions. So for here, we are doing in the most basic type because we already calculate the mean of each candidate, and which means we can plot it just as identity. Nothing changed. The height is already available, which is the mean of each candidate. Then there is another question. So currently the bar plot looks quite messy, right? Suddenly tall, high, suddenly short. Like, how can we group inhibitors and activators together such that this one looks more like, looks more cleaner and better? So the hint is that I just told you how to do this in figure 1. So for those who are a little bit confused about like how to do this, let me state the question another way. Like what I want, like by grouping inhibitor and activator together, what I'm actually trying to do is just to change the order of how each candidate is plotted, right? It's really not about measuring the height of the bar plot and group them together. It's just about what's the order of plotting out each candidate. And whenever you want to ask ggplot to change its order of drawing out stuff, you specify that column as a factor and use the level to specify the order you want them to plot out. So here, because drug 002, 014, and 179 is inhibitor, so I group them together. Because drug 009 and 0559 is activator, so I group them together. And finally, I want the control at the beginning. So this is the order of the plot. And what I then do is just to make the drug column, which is the x-axis, a factor whose level is the order I want it to be plotted out. And that's all. And of course, this is the same trick we used before to change the order of how the text is displayed in the legend in figure 1. Then another thing, very important, not programmatically, but in statistical manner, is because we measure stuff with replicates because we want to reflect the uncertainty or noise associated with the measurement, which means because there is some noise, every time you measure the activity, even if you are measuring the same thing, it can be slightly different due to the existence of random noise. So typically people want to know what's the uncertainty associated with your measurement. We do this by adding an arrow bar to the bar plot to show what's the, typically there are 2 ways of showing it. Either you show the range by arrow bar of mean plus or minus 1 standard deviation of your measurement, or you use plus or minus 1.96 times the standard deviation. So for those who have taken statistics, you may immediately recognize that this is the 95% confidence interval, which means you have 95% confidence, or the probability that the true values lies within the range defined by the arrow bar is 95%. So what we can do, then in programming, how can we add the arrow bar to the ggplot is that we use another function called geom arrow bar. And this function accepts its own AES function where we specify how to calculate the bottom, like what's the bottom value of that error bar, what's the top value of that error bar, which is from the mean column and the SD column of our original data. And here we do something to the appearance of the error bar to make our plots more beautiful. Say, for example, you don't want the error bar to be super wide such that it begins to overlap with each other. Also, you don't want it to the lines in the error bar to be super thin such that the user can no longer see it. So you adjust the width, how wide each error bar is by using the width function argument, and you adjust how thick each error bar is by using the argument line width. So one thing I need to mention here is that what's the meaning of this 0.2? Like, what's the unit of it? So actually, it becomes much clearer if I tell you that inherently in ggplot, if the x-axis is a categorical variable, which means they are not a number, ggplot treats each category as an integer, which reads like 1, 2, 3, 4, 5, 6. So here, 0.2 is actually with respect to the difference between these two categories, which is 1. So when it is category, ggplot secretly assign 1, 2, 3, 4, 5, 6, those integers to them. So the distance between two x-ticks is 1. So by knowing this, you can have a sense of what you need to put. Say, for example, if you put something like 1.2, then it's wider than the distance between two categories. Then your bar error plot, like error bar, begins to overlap with each other, which is a bad thing. Okay, so here is the last homework for those who need to take this course for grade. So my previous way of specifying the order of the bar plot is by typing out the name of each category one by one. So imagine we run a much larger drug screen and ends up with something like 200 candidates. Are you going to type them out one by one again? So it's super tedious, right? So how can we have some code that doesn't require us to specify, to exactly type out the name of each category, and but still allow us to specify the order of how the bars are plotted out? And to make things even more complicated, I want you to still preserve the order of within a group. Say, for example, within the inhibitor, I want the drug number to gradually increase from 002 to 179, rather than randomly organized, like pop up, like 2, 179, and then 14. So, and to make things even more complicated, now I want to assign different colors to the bars belonging to different group to make it even more beautiful. So control, this bar needs to be gray. The inhibitor bars need to be blue. And this bar needs to be my favorite color, same. Yeah. So how do you achieve it? So the answer will be, for those who don't need to take the course for credit, feel free to do it or not do it. The answer, anyway, will be reviewed 2 weeks later. Yeah. Okay.
I'm just checking, the homework is this one and the one you gave on date.
Yeah.
So 2 pieces of homework.
Yeah. I will give you a summary of all the homework you need to do by the end of this class. Yeah. Oh, sorry, like after this class ends, I will send you an email, like for those who need to take the class. Okay, so there are multiple ways of doing this. Some may be very complicated, some might be very easy. If you learn this course well, you should figure out the easiest one. Yeah, so how to do this homework? So first, I recommend you to work along only based on what we have learned in this class from day 1 to day 3. If you forgot how to use some functions, feel free to read the documents, but try not to ask AI to just immediately generate the codes for you, or like begin to ask someone else in the forums to see how to do it. If after some trial you feel it's a little bit difficult, you need some inspiration, you can ask AI how to do it. And then this practice you how to phrase your question to AI and how to torture the AI to give you the correct answer when you don't know the solution to an answer. And for students who need to take this course for credit, the only thing I don't allow you to do is copying like results from your friends. Yeah. Trust me, there are actually many ways to tell whether you copy the code or not. Yeah. Okay, so one final thing is that nowadays, because data manipulation, by the way, this data manipulation is not like manipulating a data frame. It means sorry.
When you said not allowed to copy from your colleagues, are you allowed to copy from AI or no?
AI definitely is allowed. Yeah.
Okay.
Copy from AI is allowed. Yeah. So nowadays, because data manipulation, the process of like Photoshop your data to get it published is such a severe problem, and some bad practice of collecting your data until p-values become significant is so severe in the field. Many journals require you to not only show the error bar, but also show the raw data points, the raw data from each replicate overlapped on the bar plot you plot. It's a good practice, and because, say for example, behind an error bar like this, it can be like 3 points like distributed quite like a normal distribution. It can also be like a few points concentrate really close to the mean, and then suddenly another outlier very far away from the mean. And even if they converge to the same error bar, that's completely two different questions, like two different stories. One means that your measurement have some noise. The other means your measurement has to be super precise for a period of time, and then suddenly there will be an outlier pop out. So this is two completely different story, and can only be seen if you overlap your raw data for generating the mean and standard deviation onto the bar plot. So how can you do this? So I mean, essentially using it's adding some point. Then let's use geom point. So there is a problem with using geom point. That's because geom point will place the point exactly at the center of each group. And when the y value is also close, then you get points overlap with each other because they are so close to each other. To solve this problem, we use another function called geom jitter, which is also about putting points onto your plot, but this time you can give some random displacement to the point in the direction you want, such that they no longer overlap with each other. So the way to use geom jitter is, again, first give it the data it needs to plot, and then the AES, and then here are the two important arguments. The width and the height. So width means like how far away do you want to on average displace, randomly distribute each dot, each point on the x-axis. And the height means on average, how wide do you want to distribute the point, randomly jitter the point in the y-axis. So here we need to set height to exactly 0 because the y-axis value carries very important meaning, which is the value of your replicates, the reads of your replicates. So you don't want anything to add anything random to it. But the x-axis is fine as long as it falls within this bar. It's fine. So that's why we introduce a 0.3 width and height equals to 0. And here you see another function is set.seed1. So this is because the geom jitter use some random process to scatter around your points. So it's like rolling a coin or throwing a coin or throwing a dice. And this makes some annoying behavior because every time you click ggplot, the distribution of these points will become slightly different, which makes your plot a little bit irreproducible. Sometimes you get very good random scattering, sometimes you don't get. So to avoid this annoying behavior, you can use this function called set.seed1. You can also, it just means set the random seed to 1. And you have lots of different random seeds. You can also set random seed to 5, 6, 100. And this means R will always use the same random numbers to generate the scattering such that your plot is always reproducible. One trick you can do is that you try some different random seed until you find the best appearance of geom jitter. And then you fix that number and your plot will always be beautiful. Yeah. And perhaps one thing finally, coming back to a very important topic. You see here, I pass a different data rather than our original data. So it's called, instead of all candidates, I pass another thing called all candidates long to the geom jitter. So first of all, the geom function in your ggplot function indeed can use different data and different aesthetic. Previously, we only specify it in the ggplot core function, which is here, because all the following geom function will use the same data set and the same asset. Here, we re-specify it because for geom jitter, we need to use a different data set and a different x and y axis. And why is this? Is because this. So in our, currently we are using, I need to remind you. So currently we are using the wide data frame format to plot out all the previous plots you have seen. But the problem of making a geom jitter plot is that we need to specify a y-axis, which contains a column for the y-axis, which contains all the y values, all the reads of each replicate. But in our wide data frame format, for user friendliness, we make it into 3 different columns such that all the replicate can be shown within 1 row. But ggplot says, no, it's not friendly to me. For whatever y values you want to use for the geom jitter, it must be in the same column. So how can we deal with that? So we use pivot longer to reshape our wide format into long format such that the y values we want to use now appear in a single column, and we can pass the name of that single column to the y argument in the aesthetic function. And then we can plot the geom jitter without any problem. So as a visiting back to when we introduced pivotal wider and pivotal longer. So what's the use of pivot longer? It is useful when you use ggplot and you find you need your values you want to use for a specific axis is actually distributed across different columns. In this situation, you should immediately realize that, oh, I need to use pivot longer to squeeze all those columns into one single column such that I can use my ggplot function to specify which value to use for that axis. Yeah, so in other words, wide is easier for people to read, long is easier for ggplot. Yeah. So one final thing, so far, if you run the ggplot function, it will, the plots will just pop up in the lower right corner of your RStudio panel. But I mean, this is useful when you are still troubleshooting the appearance of your plots. But when you fix the appearance of your plots, you want to export lots of images to a specific folder, then it is easier if you can just programmatically asking R to draw that image directly to the folder you want. So how to do this is that we use another function, two other functions, png and div.off. So div is just abbreviation for device. So the png function is for plotting a png. If you want JPEG, BMP, or TIFF, you can also use the corresponding function.
Is there a vector output?
I think BMP
Like
is.
SVG or something?
You can check. Yeah, I think there should be one. Yeah. So the grammar looks like this. So at the before you call your ggplot, you put png, the relative file path, full file path, or file name of the png you want to create, and then how wide the image is, how high the image is, what's the unit of height and width. Here I use px, which is pixel, which means my image has 1,500 pixel in width and 1,500 pixel in height. So it's essentially a square image. And finally, the resolution, which is in the unit of PPI. And then once you run this function, it creates something called a device. You can think it as a canvas where you can begin to paint. So you use ggplot to paint your plot onto that canvas. And when you think you finish painting, you use the device.off function to close this canvas such that when you are using another ggplot, it will be plotted onto a different canvas rather than the current one. So device.off kind of finalize the plot, and you will see it in the folder you specify here with the exact name you specify. So to conclude, we learned a lot of functions and different packages in the tidyverse. So what you essentially do with them is that you use reader, per, dplyr, and tidyr to shape, analyze your data. And when you feel that you want to visualize your data as a graph, then you use all those functions in the ggplot2 to visualize your data. So let's go to the section 6, which is some advice I will give you on how to write readable and maintainable codes. It has nothing to do with a specific function, a specific like codes in R. So it's just a good practice of how to write code. So here is a 3-line point you should avoid in your future life when you begin to write codes. So when I might write my code, only God and I know how it works. 1 month later, only God knows how it works. Yeah. So this is a very typical situation. Like, to be honest, even those big tech companies like Microsoft can still suffer from such kind of problems where they find some codes written by some employees are no longer understandable by other people in the company. So, and this comes to the question is that, isn't it enough if my code is already running. So it's not, because first, even if your code is running, there is no guarantee that it's running in the way you intended to run, as it can still contain some logical errors. This turns out to be very important because you may introduce artifacts, or the conclusion you get is based on a wrong process. So the conclusion itself is wrong, even though the conclusion pops up without any error messages from R. And I mean, it's quite often that other people, like your collaborators, your lab mates, need also to use your code. If it's not very easy to understand, it would be very difficult for them to use. And during the peer review process, it's also hard for other people to point out your logical errors if they can't even understand what you are writing. And finally, the most important thing, although you may not believe at this point, but it can really happen, is that if you write a code in a very terrible manner, and then you throw it away, like work on another project for a few months, and then you go back, you will think only God knows how it works, because even you yourself no longer understand how the code works. That means how to avoid these problems is that use some good practice to write a readable and maintainable code. So tip 1 is use comments. So comments, as I mentioned before, is whatever appears after the number sign. RStudio will highlight it as green, which means it will never be seen by the R language when you run the code. So it doesn't make your code slow. Yeah, I need to repeat, even if you write lots of comments, it does nothing to the speed of your code. Yeah, because it's ignored by the programming language at the right beginning. Then the purpose of comments is for human being to read that and together with your code, such that they can understand what each line of your code is doing. So then here comes the problem. Should I comment each line of my code, or where should I comment? So first, at the beginning of the script, do a brief comment to explain what this script is intended for, what it is going to do. So it's like an abstract when you write a paper. And then whenever you feel the code is not immediately clear by just reading it, try to add a comment. So there can be two situations. First, the code itself is difficult to understand. For example, you use a function that's not very widely used, and you feel that the function name does not directly explain what it is doing. Then add a comment to explain what this function is doing and why are you using it, instead of trying to hope that the reader, they themselves will figure it out, although they can if they take my course. But yeah, it can be difficult. But you can solve this problem if you directly write the comments out to give them some direction. Another situation, which is more frequently overlooked, is although the code itself is very easy to understand, say for example, reads equal to reads minus 1. Okay, you just minus 1 from the reads and assign it to the same variable. But the problem is that the purpose of why you are writing that line of code there is not clear. Say, for example, why are you going to minus 1 from your reads? Is it for correcting some background? Is it for making some conversion such that you want your reads to start from 0 rather than 1? Or is it for other reasons? So for the users, it might not be immediately clear to them, why are you doing this minus 1 here? So that's another situation. You should comment your code to explain the purpose of the code, even if the code itself is very easy to understand. And the second tip is that you have the freedom to name your scripts, your function, and your variables, of course, as long as you stick to the rules of like no space using, do not use keywords. But still, it would be very helpful if you can try your best to make the name meaningful. Say, for example, for a script, a bad name is something like, oh, my script 2. And oh, today I write this script, so I name it as the date of the script. Instead, try to briefly explain what it is doing and what's the version of it in the script name. For variables, this is the most important thing. Try to avoid using random meaningless numbers or letters like A, B, or my variable, or some abbreviation that no one can guess out what it is for. If you really want to do it, then at the beginning of your script says that throughout this script, this variable name is an abbreviation of blah, blah, blah. Here is some good example of variable names, which clearly indicates what is inside the variable or what this variable is intended for. And for functions, again, very similar to variables. Try to make the function name you customize meaningful. And it is okay for you to use abbreviation if you believe that abbreviation is very commonly used. Say, for example, log2fc, rather than the whatsoever DSDW, which perhaps is something invented by your own. So fine, the tip 3 is make your code expressive. So even if you use good variable name, so even if you write a lot of detailed comments, it can be even better if your code itself is telling people what you are doing. So it adds an extra layer of security to your code. So first, use very meaningful variable names is part of the tip 3 because it at least allow the variable name itself to explain to the user what you are trying to do. And whenever possible, try to select your column using the column name rather than an index, because if you are using a column name and your column name is named in a meaningful way, then people can immediately know, oh, what columns you are selecting. But if you are trying to refer to it with index, then people need to go back to the data, which is not always easily accessible, and say, oh, what's the second column? What's the third column? Right? And another thing is that if feasible and not too difficult, you can rewrite for loops as by vectorization as a simple line, which makes it very easy to understand. Say, for example, here is, oh, what is NA in the read column, and let's sum them up to count the number of NAs. Yeah, so packages like tidyverse are very good examples of writing a code in an expressive manner. So use it and learn from it. Another thing I typically see is, especially among people who first use R for first time, is that it seems there is some black hole preventing them from opening a new script to write something different. Like for the first script I teach them to write, 1 month later, I find 1,000 lines of code in the same script. So nothing will happen if you open a new script for different projects. I wouldn't charge you money for a new script. So try to avoid examples like R codes for my PhD thesis, which contain 2,000 lines of codes. Instead, trying to break up a big scripts into smaller chunks, into smaller scripts where each of them have a well-defined function or target. Say, for example, like drug screen analysis, single-cell RNA-seq analysis. And when you are doing this, you are actually doing something called modularization, which means your code is now into different modules. Say, for example, later, if you want to analyze single-cell RNA-seq data, you can just get out the single-cell RNA-seq script and then repurpose it for other purposes, rather than go into your 2,000 line script trying to find where the single-cell RNA-seq data analysis part is. So one final thing, this is the thing I think I really regret a lot, I don't like realize it early enough, is exert version control. So we frequently, based on our needs, we need to update our scripts. Like we think, oh, this might make it better. So whenever you want to do this, ask yourself, is this a big update or not? If it is a big update, try to put all your codes into a different scripts and mark the version number of it rather than directly modify your original codes, because we never know whether this intended improvement or fix will do the good or the bad. Yeah, it happens to me multiple times. I was like, oh, this will definitely make it much better. And then after 1 week, I figured out, oh, actually it doesn't. And because I modify my original code, I need to think what I write 1 month ago for version 1 of my code. And sometimes I can never reproduce it. Yeah, so do exert careful version control. So if it is a very small change, you don't think it deserves another script, you can also comment your original code such that it becomes a comment, which will not be wrong, but then write your new codes down below that comment. In that case, if you want to go back to the original one, you just delete the current line and decomment by delete the number sign, so your old code comes back. So GitHub, as you might have heard or not, is a very powerful tool for version control. It has some learning curve, to be honest. That's why we don't have time to teach it here. But when you think you get more advanced and comfortable with coding, I highly encourage you to learn how to use GitHub to do version control. So many big tech companies are also using GitHub to perform version control, such that you can keep a track of all the versions available. And whenever you feel you need to roll back to certain version, you can easily go back. So tip 6 is, if you develop a script that is going to be a workhorse, widely used or heavily used throughout your PhD or across your lab, then in this case, it might warrant an extra layer of protection against confusion, which is a separate technical documents in addition to comments. So in comments, we can only use text, but if it's really important script, you can write a separate technical document like a Word or PDF, where you have images to illustrate the design principles or use more words. You can also have bulletin points, all those kind of stuff you will use when you are writing a user manual or protocol. So what you should cover is that some background knowledge. If your code involving some like mathematical concepts or physical concepts, the design principles, usually you can illustrate it with a graph, so it's much easier to understand than text. And you should also include a few examples of how to use your script. It is for other people, it is also for yourself, such that even if you get the code 10 years later, you can still understand what am I doing 10 years ago. So what is a good, we don't have time to teach you how to write good technical documents again, but MATLAB, another programming language, is well known for its super beautiful technical documents. So even if in the future you don't plan to use MATLAB, I recommend you to read the technical documents MATLAB write for each of its function and toolbox or package to see how to write a good document. So MATLAB is a charged programming language. The fee is non-trivial, but many people say that even the technical documents itself worth the fee, the subscription fee of MATLAB. So finally, section 2, a very small section, just to introduce 2 more tools, like for you to write your code if you like it in this manner. So the first one is called R Markdown, or like another name perhaps more familiar to you is Jupyter Notebook, if you have seen some people using it elsewhere. So it's like write your code, write your code like a report rather than a script. So what you do is that you insert this. So what you do is that so first the first chunk, no need to care about it. It is just a way some codes to make your codes look like a report, and then you begin to write your codes or separate your codes into separate chunks, which can be run separately by clicking this play sign. And at the same time, you had a description for each chunk of the code. So this is perhaps more clear if I illustrate it in the RStudio later. Maybe I should just illustrate it now. So. Okay, so here is the interface for R's markdown files. You can immediately see how different it is organized from the from a script. Also for those on Zoom, if you don't see it, just let me know. Yeah. So and clearly, so it here, it might still not be very clear, like what's the point of using an R markdown file, because we are still at the source level, source layer, which means we are using code to design the markdown file. If we click the visual, I think you can immediately get what's the meaning of using R markdown file. So what it does is it essentially make your code look more beautiful. I think I have said something wrong, but anyway, it's okay. So I guess I should just, sorry. Sorry for that. Oh, sorry, it's just a title here. Yeah, perfect. So what you can do is that you can collect each chunk of code to run it, and the output will immediately display. Like you can immediately preview the output and what you read in, and then when you draw a plot, it will immediately pops up underside your corresponding chunk of code. So it looks like something, it more look like a report that's easier for people to read, and many people really like it, rather than a script where your code is code and the output flies to everywhere. So some people really like this style, but I should say that, sorry, but I need to add that it's not always good. Yeah, So our markdown file is not meant to, for those on Zoom, we now switch back to slides. If you don't see it, just let me know through chat. So our markdown file is not to completely replace script. So it is a good choice when you want to give people an example or illustration of how your analysis is working. But all it is a good stuff if you are just doing some very preliminary explorative work on your data set. But when you want to do some really workhorse job where you need to batch process lots of data, or as you may learn later, like if you want to run some really heavy duty tasks, requires a lot of CPUs and RAM on a server, like our UCLA's high performance computer, Hoffman 2, then script is still your choice because the markdown file has lots of features intended for easy reader, to be easily read by readers, but they all become some troubles when you want to run it in a batch manner by the computer. So all in all, illustrating your idea, you can use R markdown if you like it, and but for workhorse job, you should still use script. And the second tool I want to introduce to you is the R project. So R project is just a way for you to organize your scripts and outputs. So you have seen, so far we have scripts, which is the code. And then during the analysis, we will output like images, CSV files. These are our outputs. And of course, we also have our data. So in a project, you typically will have data, scripts, and outputs. So how do you organize them? So it's also a way of make your overall design clean. So my typical way of organizing it is first, because I need to collaborate with lots of people. So today I work on like pancreatic cancer. Tomorrow I work on liver cancer. Then 1 month later, I work on zebrafinch brand. So there are lots of projects I need to collaborate with other people. If everything is combined in the same folder, then my brain will explode because I never know where to find the correct file. So usually I first give a name to each project and then create a folder for them. And within the folder for each project, I have the data, the scripts, and the results folder to hold the corresponding items. And our project is just a way to attach the concept of a project to your folder such that the working directory is automatically set to that folder. So you remember, like, we need to set working directory at the beginning of our script to our current folder to avoid using all those very long full paths. The problem is that later, say for example, if I share this folder to another collaborator who's using a different computer, then he needs to change the full path in the set working directory to his like full path on his computer. So this is a little bit annoying. And also for you, when you are switching between different projects, you also need to set the working directory to different folders corresponding to different projects. That can soon get annoying if you are working on a lot of projects. So what you can do is that you can create an R project and connect it to a specific folder such that when you open that R project, your working directory is automatically set to that folder. And when you share this R project with other people, when they open the folder, they automatically set the directory, the working directory, to that folder on that computer. So you no longer need to worry about changing the directory. So again, so these are just some useful tools. If you want to use it, feel free to use it. If you feel that you are not ready for it, or you don't feel it help you that much, feel free to not use it. So the conclusion for the whole lecture. In section 1 and 4, we introduce very important concepts that holds true across all programming languages. Make sure you fully understand this part. This is the most important part of this lecture. In section 5, we introduce a very useful package in tidyverse. And it's okay if you forget all the functions in tidyverse. Just keep in mind that whenever you want to analyze some data frame in R and visualize your results, just keep, the only thing I ask you to memorize is the word tidyverse. Yeah, that's all. And section 6, so I give you some tips on how to make your code more readable, more maintainable, such that hopefully you don't find yourself not understanding of the code you write 1 month ago. And section 7, we introduce 2 useful tools in R, like use them if you like them. If you don't want them, it's your choice. So we have 10 minutes left. So let me just show you how to create an R project. Share the screen. So for those people on Zoom, now we just switch to the RStudio interface to show you how to create a new R project as mentioned in section 7. So in the file section, if you go to new file, you can create a new R script, but this is not what I want to teach you now. Instead, below the new file, you have an option called new project. So just click it. Okay. And it will ask you to whether you want to save the current working, it just like whether you want to save all those variables or not. For me, I just choose not to, but then we can create an R project. You can choose a new directory, new project. Then you can just type in the, like say, for example, the folder name you want. And the next part is say, create this project as a subdirectory of. So you can browse here. Say, for example, let's create it in our QC Bio lecture folder as a separate directory as our project demo. So it will ask you whether you want to create a Git repository. So it's not applicable here for this moment. Yeah. And then we create it. So there will be some waiting time. And then RStudio will switch us to our new R project. So one thing I want to point you is that now our working directory, as shown here, is automatically switched to the current folder or the current R project. And then we can put in script, files, codes, scripts, output images, output files, your raw data, all into this R folder project. And because the working directory is automatically set to this folder whenever you move this R project to, so you never need to worry about set your working directory. So of course, there are other advantages of using R project. For example, it also makes it much easier to do version control, and even more powerful, you can combine it with tools like GitHub, but at this moment, it's a little bit too advanced. But still, I want to let you know that such a good tool exists, that is R project. Yeah. So you can simply treat R project as a folder. So once you create it, it's a magical folder. Whenever you open it in R, it will always set the working directory automatically automatically for you. Yeah. So that's all I want to teach you for these 3D lectures. For those students who need to take this class for grade, I will soon send out a summary of all the homework you need to do to everyone. And for those who need to do this for the grade, please also read carefully about the policy of doing the homework. And the answer will be reviewed 2 weeks. Yeah, in 2 weeks.
So I saw that you said the due date was October 31st midnight. So you mean Thursday night, like
Yeah.
Friday. So Thursday night it's due.
Yeah.
The 30th.
Yeah.
Okay.
Also, if you are a little bit late, I don't mind. Yeah, to be
Okay.
honest. Yeah. Yeah, as long as it's not something like 1 week late, I can tolerate that. Yeah. So yeah, but try to be on time. Yeah. Okay. Yeah, that's all. So yeah, class dismiss. Yeah, I'll stop.
Thank you.